Let's see, 2, 3, 4. Okay. Okay. So let's see. Let me get done here. Yeah, let me get this, guys. Okay. All right. All right. Welcome, scholars. So I have that it's that time. Anybody that shows up now, I'll just check attendance again around 2:15. It's no real major announcements. This is College Algebra 1. So just as long as you all are just making your way through our assignments on Pearson, that's linked to our Blackboard. As long as you're making your way through those documents, you're fine. Just as a reminder, I made anything that you see me writing, I've made the PDF copy available for all our lectures. It's in Blackboard. You can find it there under the folder that says box link. You'll find it there. So again, at the end of each session, I'll create a PDF and I'll load it pretty instantly. As usual, this is a remote asynchronous. So if you've gotten into the Zoom call, that means you've gotten your attendance credit and you're not obligated to stay. And so my intent for today is to go through as many homework questions together as we can. If you want me to go through specific questions, the best use is to make use of the ask my instructor and to just bring it to my attention. I'll pull it up and we can talk about it. Otherwise, I think I'm gonna just go ahead and hop into the material for the day. Also, if you have questions, chat periodically, but for a faster response, just unmute yourself. So our assignment today comes from section 1.4. I think on Monday we did the lecture. We did as much of the lecture corresponding to this. And so here we'll go through as many homework questions as we can. All right, so here we're asked to write a linear function that has the indicated values and sketch the graph. So let's take some notes. Let's start by taking some notes. Yeah, you have to forgive me. Like my energy is shot. I don't know if it's just because it's later in the day or I'm getting older. Typically am up throughout the night. Maybe my lunch was too big. That happens a lot too. But I try to, since I get the itis so easy after lunch, I try to eat light, you know. I try to. Sometimes I just feel like, forget it. I want some Publix wings. That's like the best wings. Because they're inexpensive and they taste really good, but you just got to be careful. Okay. So write a linear function, right? So whenever we're working with lines, we have 3 formulas that I usually like to have on hand, but for these, I've noticed that I've really just been using 2 of them. So I typically start with like the slope formula. So we have our y2 minus y1 over x2 minus x1. Again, this is our slope. And then if we're doing a linear function, it's f of x. It's similar to the y equals mx plus b, right? And let's identify the ordered pair that's been given to us. What piece of information has been given? So we want to find the line through these 2 points. So these are ordered pairs. So the first one is saying that when x is 0, the corresponding y is 9. And when x is negative 9, the corresponding y is 0. Okay. So personally, whenever we have ordered pairs like this, I like to just label them x1, y1, x2, y2. All right. So then that makes it fairly simple to plug them into, let's start off with the slope formula, finding the slope between 2 points. Okay. So our y2 is 0 minus our y1 is 9 over negative 9 minus 0, right? And this is our slope. So it looks like it's going to be negative 9 over negative 9 which is 1. Okay. So then let's take this and take a point. I'm going to choose the first point that's 0, 9 and plug it into the other equation. So our slope is 1. X is going to be 0. We're solving for b. And the corresponding y is going to be 9. So then, you know, you can quickly see that our b equals 9. They gave us our y-intercept, right? We didn't even really have to do all that, but they gave us the y-intercept. Okay. So then putting these two pieces of information together into our linear model, the slope was 1, so 1 times x, which is just x, plus 9. Let's see if I can I still paste? Nope. Style. This one. Let's copy. Okay. And then before we submit it, let's just confirm that our given points, come on. Let's confirm that the original points work here. So when x is 0, y is 9, so that checks out. When x is -9, y is 0, so that one, these two check out. Okay. So now let's go back to Pearson. Type an expression. So f of x, I think we said it was x plus 9. Okay. So then our y-intercept is 9 and our x-intercept is -9. And I think the only one that does that is C. We're going to go with that one. Okay, let's try another one. Let me see the time. So similar, right? Let's work this one like we did the previous one. Let's see what kind of changes we can catch. There's that. Come on. All right. Okay. Come on. Sorry, guys. There it is. Okay. Okay. So one of my instructors would say, every time you use a formula, write it down. So let's rewrite all that stuff. y2 minus y1 over x2 minus x1. This is our slope. We want to finish y equals mx plus b. Let's identify the order pairs that were given. When x is -1, the corresponding y is 1. When x is 2, the corresponding y is 13. So notice it did not give us the y-intercept here, but that's okay. Let me see the time. Okay. Is that right? Looks like it. Okay. So then we like to label x1, y1, x2, y2. Okay. So then if we're finding our slope, that's going to be 13 minus 1 over 2 minus a -1. Notice my use of parentheses. So it helps me to keep track of my signs. Those signs are very easy to overlook, and you'll miss it if you don't make sure to account for it. 13 minus 1 is 12. A double negative becomes positive, so that's a 3. So this is 4. So we have our slope. I'm going to choose the first point because it just looks like those values are easier to work with. So then if my slope is 4, our x is going to be -1. We're trying to solve for b now, and the corresponding y is 1. Sorry, guys. Okay, so then we get -4, so then add 4 to both sides, b equals 5. Okay. So we have our slope and our y-intercept. So then our f of x should be 4x plus 5. And we want to check this before we submit it. So in order for this to be the answer, we're saying this is linear because, you know, the highest exponent is a 1. But we want to confirm that when x is -1, let's see. So we want to confirm that when x is -1, the corresponding y is 1. When x is 2, the corresponding y is 13, right? So if you put in -1, that's going to be -4 plus 5, which is 1. You see it here, it's checked out. When x is 2, 8 plus 5 is what, 13? So that one checks out as well. Okay. So we have a linear function where those two original points are on the function. We got 4x plus 5. Hopefully they're not trying to make us start working on a different question. Oh, it looks like we got booted. Let me see. Okay. All right. Let me see. Let me just restart the system. I'll be right back. It seemed like it went through that time. Let's just see. Yeah. So we may have lost the work that we were working on, but that's okay. This one, well, this should be the 2 o'clock. This one, it doesn't matter. This one. I think we're working on this one. Okay, 2 and 7. So,
can you let Addison in? He gotta be late in the meeting.
yeah, I'll get him in just a moment. Okay, let me. Finish this one out. So I have to redo this one. Okay. And then it might be because my device is plugged in, but it's 2 and 7. Let me finish this one out. Okay. So -1 and 1, and then 2 and 7. Okay. I'm just trying to finish this one because like it just seems like my device is just like throwing a tantrum. Okay. Let me do this one more time. Okay. And then I like to label. Then our slope. Uh, 6/3, which is 2. Then we're going to take this and solve for a y-intercept. So then our x, we're gonna let x be -1. That's not a 1. I don't know b, and the corresponding y should be 1. So then b should be equal to, that's gonna be a -2. So then you add it, that's gonna be a 3. Okay. So then our function (2x + 3). So I can still paste. Okay. We got 2x + 3. I'm just gonna go with it just for the sake of time. This one. Come on. Simplify your answer. We got 2x + 3. 2x + 3. Okay. Our y-intercept is 3 with a slope of 2. So it can't be A that has the wrong y-intercept. It can't be C and D because those both have a negative slope, the wrong slope. So I'm just gonna go with B. Okay. So let me hop back over here, stop. Let me see. All right. Okay. Chat. Let me see. Okay. Yeah, but yeah. So there was a thing in the chat that said we get like that most days. It's gotten. I don't know if it's just me or not, but it seems like the whole sleepy thing has gotten way worse at this stage of my life. And I don't know if it's just because I'm older or not. But when I talk to, again, I don't know if talking to my friends is a good source because we're all the same age. So, and there a lot of them are older than me. So, but they experience the same thing and they just get super sleepy. So I don't know if that's some part of the ascension process or what, right? But it is what it is. We just do the best we can and keep it moving. Do our best. We get your rest. Don't stress and be blessed. Okay. All right. That's what it is. Okay. So we're on to this one. We're asked to find the intervals over which the given function is increasing, decreasing, or constant, right? So here, let me see. Come on. Okay, that's fine. Okay. So here, you can look at the graph, right? Notice the highest exponent on any variable is a 1, so this should be a straight line. The y-intercept is -2, and it has a slope of -4. All right. So as you trace the left to right, the graph is going to be going down. It's going to be decreasing across the entire domain. All right. And so with this being a line, the domain of a line is going to be all reals. So this function is never increasing and is decreasing over the entire rails. So I'm going to say parentheses from negative INF to INF. Nope. I'm typing down. There we go. Okay, let's go with that. It's never increasing, it's decreasing over the entire rails. Okay. Let's try another one. Is this the next part? Yeah, okay. It's constant, it's never constant anymore because it's always falling. Okay, next question. Find the intervals over which this function is increasing, decreasing, or constant. So we have 2x to the power of 3, right? I think so far, the main way that we have for graphing, you can choose several values of x, find the corresponding y. This is one of our basic functions in our library of functions. So this shape, the generic shape here is like an S. It's like, so as you come from the left to the right, it's kind of increasing. It looks like the left-hand side of an upside down parabola, but then when it hits the origin, it shifts or it inflects, and then it goes back to curving up. So then it's like, it looks like the right-hand side of an upward facing parabola. But in either case, as you trace it left to right, this is always increasing. All right. So the interval over which the function is increasing, The domain of this guy is going to be all reals. So it's increasing over the entire reals right here. Okay. The intervals over which the function is decreasing. It's never decreasing, all right? Okay. You know, let's take a look at the graph real quick since we have our calculator here. Thank you. Okay. I feel like I got a second window. Whatever it was, it finally went on. So if I go to my upper left-hand corner, click on y equals, we got this 2x to the power of 3, okay? Let's look at the graph. Notice, as we trace it left to right, it's going up, 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 up. It looks like it flattens out at the origin, but it actually does not. So this is a little bit conceptual. If you weren't sure, you would have to like choose points that are really close to the origin and, you know, maybe find a slope between them. You know, just, you know, you have to convince yourself that it's always increasing. You're not going to find an interval where it's flat for this example. So decreasing, there's no interval or constant, is no interval where it's constant. Okay. Nope, that's not what I was trying to do. Thank you. No interval where it's constant, check. Okay. All right, so then this example gets into where we were discussing even, odd, or neither. So even, one of the ways to express even means y-axis symmetry, right? So if you were looking at the graph, if you cut along the y-axis, one side is going to be the mirror image of the other, right? If it's even. Odd means there's origin symmetry. So the way I originally used to visualize origin symmetry, if I had a graph that passed through the origin, I would cut along the x-axis, put my thumb on the origin, and rotate it 180 degrees, right? So it's like when you do that, the top half matches exactly with the bottom. Origin symmetry, another way to visualize it or conceptualize it is that whenever you have any point x comma y, you also have a point negative x comma negative y. All the points on our graph are equidistant and mirror images of each other around the origin, right? So that's what we mean by origin symmetry. Every time you have one point, you automatically get another one that's the same distance away from the origin and is mirrored across the origin, right? Okay. So in this context, we need to kind of rely on the definition. So we have about 3 ways of explaining how a function is even, odd, or neither, right? We kind of just discussed too with the looking at the picture. What's the other technique? Well, because I think it might actually just be 2, but that's okay. But here, what we're going to do is we want to apply the definition of what it means for a function to be even, odd, or neither, right? So what we mean is the definition of a function being even means whenever we evaluate f of negative x, we get back to the original f of x, right? For odd, whenever we evaluate f of negative x, we get negative times the original, right? So then we need to see if we can invoke one of those 2 cases. So I think it was the pictorial representation or the ordered pair representation. And then the last was the actual definition of even and odd. The ordered pair is like whenever you have x comma y. For even, you would also have negative x comma y. For odd, you would have both the x and y would change signs. Okay, I know that's like a lot of audible stuff. So let's see this one in action. So all we're doing is like looking at these data and like comparing them. Like if you look at the first one, you have negative 129, but then if you look at the last one, it's the same 2 numbers, but the signs have been switched. Both the x and the y, the signs have flipped. And then I think if you compare the rest of them, both x and y's, the signs have been flipped. So then that's an indication that we're working with an odd function, right? Whenever we have x comma y, we change both the x and the y, right? So that's kind of where that comes from. Okay, let's try another one. So we're tired. Come on, devices. I think it's time for me to get some new equipment. Let's see the table. Okay, so even, odd, or neither, right? So now if we look at this one, I think we still got the same thing going on. If you look at the first order pair, they're both negative. Compared to the last one, then they both become positive. So even though we have the same data points, the signs are flipping both for both the x and the y. So that's an indication that we're working with an odd function. If you were to plot these points, they should be mirror images around the origin, and equidistant from the origin and reflected about the origin. And then I'm experiencing this weird experience where I feel like it's coming from talking too much, but it's like my mouth is getting dry. And I know if I go drink water, it's just going to make it feel more dry. And that's like alkaline water. So I was like, I don't know. Determine algebraically whether the given function is even, odd, or neither. So now let's see algebraically, right? So graphically is where you basically, if it's on the y-axis, you will cut and see if they match up. Or that thing where I was saying cut along the x-axis with your thumb and rotate by 180. That's a visual representation for odd, a function that we consider to be odd. But let's see this in action algebraically, right? So let me get a copy of this guy. And just filling the air while I try to get this image to look proper. I discovered a new snack. I really like chips, but I do acknowledge that like they just cause a lot of trouble in my body for what I'm trying to do. So I came across this new snack where it's basically like a raw bell pepper that you cut into like, I did jeweled where it's like thin strips, but that was too thin for me. So I cut it thicker, and I ate it with hummus, and it was actually good. I was like, wait a minute. I didn't, because bell pepper is very pungent taste. And then, but my friend was like, yeah, just eat it with some hummus. And so I was like, let me try it. I was like, oh, I think I got a new healthy snack. I was like, so I'm all geeked about that, Anyway, just feeling the air while I was getting this question set up. Okay. So this question comes from section 1.4, question 25, right? So algebraically, to determine whether a function is even, odd, or neither algebraically, you got to use the definition of even and use the definition of a function being odd, right? So the definition of, come on, every time I go to write, it's like lagging. I think I got to unplug it, and I think that's what's doing it. But I was trying not to unplug it because my battery's a little low. But it's okay. So the definition of a function being even means that when we evaluate f of negative x, we get back to the original. The definition of a function being odd, when we evaluate f of negative x, we get a negative times the original. If we can't get to either of these cases, where we get back to the original or we get back to negative times the original, then it would be odd. It would be neither. It would be neither. Okay. So let's apply this to the one that's the equation in question. That was a mouthful. So we want to replace each x with negative x and then simplify and see and interpret the results, right? So what I like to do is first replace each x with a blank parentheses. Got to create some space. If you're holding on to your x, then you haven't created a space to allow for something better to come in if you're still holding on to energies that don't serve you, right? That's so like such a tangent, right? Because we're talking about x's as in the letter x, but for some reason, it seems like a lot of stuff that we do here correlates to like life experiences of dealing with x's. It's just so weird. It's just so funny. That's why I was saying that, because it's just funny. Anyway, okay, so we said replace each x with a negative x, the opposite. Negative x, okay? I think I might be sleepy. That's probably what that is. All right. So then let's simplify, right? So if we look at this term, right? Terms are things that are added and subtracted. Factors are things that are multiplied and divided, right? So we have two terms. This is the first term. Let me do it one more time. This is the first term. This is the second term, right? Because these are being added and subtracted. So now, when we look at this negative x to the power of 3, if we have an odd number of negatives, You got to ask yourself, is that final result going to be positive or negative, right? This to the power of 3 is going to be negative, but then times this other negative out here is going to make it positive. So in this term, we essentially are multiplying 4 negatives altogether, right? So then what that does, that makes all that become positive. So that becomes positive 3x to the 3 plus 5. We ask ourselves, is this the original? Is it the original? No, right? And I think that if we try to factor out a negative from properly, we still can't get negative times the original, right? So this one is neither even nor odd. So this is an example of something that should be neither. So weird. Anyway. Okay. Hopefully that was okay. Hopefully we're all aboard and not all bored. I try to have fun a little bit. I try to. We said neither. There's a whole story there. Almost everything I do has a story behind it. I don't know if the stories are interesting. You know, I'm still working on my ability to tell stories, but there's usually some motivation, some past experience that determines why I'm behaving this way. Okay, determine if the function is even, odd, or neither. I think I can do this one just talking through it, right? So if we were to replace the x's with negative x, notice with the first term is to an odd power, so ultimately that result is going to be negative. It's the same argument for that second term. So we're going to have like negative x to the 7 minus x to the 5th, which is not the original. So then we would factor out the negative. Ultimately, we would finish with negative times the original, which is the definition of a function being odd. If I need to write that out, just let me know. But I felt like that one, you can see it. I think we got another one of these. Let's write. We definitely need to write this one out. Okay. So let's see this one in action. Get a copy first. I was sharing with my 9 o'clock class. You know, I consider myself an inventor. I have a lot of ideas for like clean energy, free energy. So, and like I don't know. I just have these things that I want to see if I can build them. You know, but it's just a matter of me getting resources and the time. You know, getting my time back on my side and not like wasting time trying to survive. Like if I wasn't wasting so much time just trying to live on a day-to-day, like just trying to get the basics, then I could actually take time to make clean energy, free energy. I mean, I have a crap ton of ideas that I want to research, like just on my own. Like I just need to be left alone, and I would see if I can get it if I can build it. But anyway, that's this whole thing. I don't want to get into it, but it's really interesting. And I really feel like I could be doing something to actually help society. But it's so weird the time that we live in, because when people do figure this stuff out, a lot of times they get killed. It's like the officials, oh, you got something that's going to help society? Oh, let's go have some tea. And the next thing you know, they just disappear like they didn't exist. I'm like, come on, these people exist. They did this stuff. So it's always interesting because I'm the type, oh, well, if they did it, I know I could do it too. Right? That's just my orientation. Then you got to think about how to share it with people without putting a target on your back. That's what I think about a lot. But it's neither here nor there. I mean, from people like Dr. Sabi, so many people that like had just such great information that would like literally transform society, and they just get killed. But it's coming to a head. It's coming to a head where it's reaching critical mass where enough people are waking up, where they're realizing how much of a farce so much of this stuff is. I mean, I got so many interesting documentaries, like I just want to share. But it's like, anyway, let's get back on task. We only got a solid 10 minutes, so let's take advantage of that time. So algebraically, right? Let's start by just having a copy of the definition of what do we mean by a function being even and odd. So again, real quick, come on, thank you. A function being even means when we do f of negative x, we get back to the original. A function being odd means when we do f of negative x, we get a negative times the original. Okay. Undo f of x. Okay. So that's the definition. These are the definitions of functions being even or odd. So we're just going to evaluate the function given, replace each x with negative x, and then interpret the results, right? So first, I'd like to start with replacing each x with a blank parentheses. And part of the reason of me going into tangents is just to shift the energy to give myself a boost, something that's interesting, that makes me think, and it gets me excited. So it's not so boring, right? That's part of the reason why I do all that stuff. Okay. So then this looks okay. So let's plug in the negative x. So we got a negative x here, negative x, negative x, negative x, okay? Like in life, negative x is like, it's rare to have an x that's like not negative. Anyway, okay. So what is this? Okay, so that's gonna be, if we look at this term here, there's an even number of negatives, so that becomes positive, all right? So this x squared. Double, for the next term, double negative is positive, all right? So we get this. Bottom, an even number of negatives, so this term is gonna be positive. 3x to the 4 and 5. We ask ourselves, is this the original? You should be able to quickly see it's not the original. If we factor out a negative on top, can we get negative times the original? And the answer would be no, right? So then this one is an example of neither. But sometimes we get questions that look like this. You know, at first glance, you can't really tell. You can't really tell until you do this procedure that we just did. We got time for like one more. This one should be neither. Come on. Come on. Oh, shoot. Okay. I don't understand why it's doing that. Yeah, I think it's Mercury retrograde. Everything is just like on the first. Or maybe I'm saying stuff that's too controversial. So then my devices are like, does not compute, shutting down or whatever. Let me see if I can get back to where we left off. I think even if they give us another one for this one, I think it's still the same result. So I'm just going to submit the result that I had, even though the question might be different. I'm totally just like taking advantage of, think about it. Because that's going to be positive. That's going to, yeah, I think it's the same result. So I think it's neither even nor odd. Okay, let's try one more. Let's see. Okay, it says the graph of a function is given to the right. Use the graph to find each of the following: the domain and range of the function. Okay, what's the domain? So in the pictorial representation, the domain is the very left to the very right. The far left looks like it's -3. So I'm going to use a square bracket. It goes from -3 up until the far right. The x value looks like a 7. 7. Okay, and I'm going to use a square bracket. Okay. And I use the square bracket because this graph is defined when x is -3, and it's defined when x is 7, right? It actually is defined at those points and really when we're close to it. So I'm going to check this. The challenge here is getting more often than not is getting a proper grouping symbol. What's the range? The range is the very bottom to the very top. The very bottom of this is going to be -2. So I'm still going to use my brackets. -2. And then the very top is going to be when y is 1. And I'm using brackets because it actually reaches these numbers. It's defined at when y is -2 and y is 1. I'm going to check this. Okay. Determine the x-intercept. Let's see. Can we? I don't know that we can eyeball this. So we might need to do some calculations. Yeah. Okay. So we have 4, 1, and -3, -2. 4, 1. I'm just gonna put a star. It's really the next question. 4, 1, -3, and -2. Okay. So basically what I'm going to do is find the equation of the line through these 2 points and then use that equation to find my x-intercept and my y-intercept. Okay. So my slope, y2 minus y1 over x2 minus x1. I like to label x1, y1, x2, y2. My y2 is -2. My y1 is 1. My x2 is -3. x1 is 4. On top, it looks like we get -3. On bottom, it looks like we get -7. So it looks like the slope is 3 by 7. Okay. I want to plug it into my f of x equals mx plus b. Okay. So my slope is 3 by 7. I'm going to choose the first point just because those values look a little bit easier to work with. So my x is 4. We're trying to solve for b, and my y is 1. So then ultimately we get b equals, let me see, 4 times 3 is 12. 12 over 7. 7 minus 12 is -5. So we get a y-intercept of -5 by 7. Okay. So then the function that I get, see the time, I'm trying to get you guys out of here. Three by 7x minus 5 by 7. We should confirm those original points, but I'm just trying to wrap this up. So if we want the x-intercept, we set y to 0 and solve. So you get 5 over 7 times 7 over 3. So it looks like 5 over 3. Yeah. So 5 over 3, right? We set y to 0 and solve. Ultimately we got to y over 3. I mean 5 over 3. Trying to wrap it up, thinking. I know this one's gonna be long. Come on. X-intercept, we got I'll just put 5 over 3. Okay. And then my y-intercept, I think it was a -5 over 7. -5 over 7. We got -5 by 7. Okay. Continue. Increasing, so as we trace it left to right, it's increasing as x goes from -3 to 4. So I'm going to use parentheses. -3 to 4 parentheses. Okay. Trying to wrap this up. I'm trying to get you guys out of here. Continue. Decreasing is never decreasing. Constant. It's constant as x goes from 4 to 7. So use parentheses. 4, 7. Close parentheses. Okay, let's go with it. Is that it? Even means y-axis symmetry. There's no y-axis symmetry. There's no origin symmetry. So this would be neither. There's no symmetry going on. Okay. So are there any questions? All right, you can access them. This is College Algebra 1, fall 2022, College Algebra 1, into the notes section, the updated daily, okay? So send it to box. If there aren't any burning questions, we're gonna end the session here. Enjoy your weekend. We'll meet next week, same time, same place. And from one beautiful mind to another, stay dangerous. Peace. See you guys. Thank you.